On a small island off the coast of Japan,
The most imperative aspect to love
is the ocean. It's the love story of a young, poor fisherman.
and the daughter of the wealthiest fisherman on the island. Despite the opposing of her father for their love,
With the power of the ocean and nature by his side, Shinji will do whatever it takes.
their love will always be. This is the sound of love.
The video you just watched consists of love, tear-inducing plot, poor acting on my part, and most importantly, a video track and an audio track. This is the camera I used to record this whole audiovisual experience so that I can present it to you. And today, I'm going to show you a lot of interesting physics and the workings of a camera. To get started, both image and sound can be described as waves in physics. What is a wave, you asked? A wave is just an oscillating behavior, whether it is the oscillation of pressure, electric field, human body, or the most common cause of waving behavior happens when the change of a system at the location affects the points next to it. In sound, there will be the compress and decompress of air at a certain location, causing the surrounding air to compress, and so the pattern repeats. Light is a little more complicated than sound, since you need to understand these, Maxwell equations, to understand the electromagnetic wave, so we'll put that to later. We perceive the changing pressure of air inside our eardrums as sound. The sound source could be anything that causes the density of air to change. It could be a vibrating string, air passing through a tube, or a pair of headphones. However, the original pocket of compressed air was created. It expands and compresses some air next to it, and this behavior repeats until the air effect propagates into our ears. The speed of wave is determined by the density and the elasticity of the medium. The more rigid and less elastic the material is, the faster sound will travel in it, since it takes less time for the material to return back to its original shape. The greater the density, the slower sound travel in the medium, because it is harder to vibrate more massive molecules. Here is the microphone that I'm talking to in place of your ears. The mechanism that is equivalent to our eardrum in this is the membrane called diaphragm that is conductive and placed next to another sheet of metal. When the diaphragm vibrates due to sound waves, the capacitance between the two pieces of charged metal creates an audio signal. The foam cover that is attached to the microphone is called a windscreen, which basically avoids the microphone from recording gusts of wind that makes an explosive noise when one is filmed outside. Another interesting fact about this microphone is that this is a shotgun microphone. A shotgun microphone is directional so that it focuses on recording the sound that comes from the direction in front of it. In this graph, you can see a shotgun microphone that records sound in front of it more loudly than from other directions. It does that by the principle of sound interference. When sound comes to the microphone directly towards the long tube, it will have no trouble traveling through it and reach the sensor. But when sound waves comes from an off-axis, it will be reflected at a different phase than itself and partially cancel out themselves. Other important aspects of a microphone are the dynamic range and the frequency range, where the dynamic range is the range of amplitudes that the microphone can capture. Sound louder than the dynamic range will be topped and below its value, and sound quieter will not be picked up at all. The frequency range, on the other hand, is the range of frequencies that the microphone can capture. The shape you're looking at right now is a graph of my voice. It is basically a graph of the amplitude of pressure of the sound waves over time. Here you can see the unit is measured in decibels, which is a logarithmic scale that better corresponds to the perceived loudness in our ears. Aside from the time domain graph that you just saw with decibels over time, there is also a frequency domain of waves. In order to convert data from a time domain to frequency domain, one we need to use a scary sounding but actually not that ungraspable method called the Fourier transform. The implemented algorithm in our computer is often FFT, or fast Fourier transform, which basically works on the principle that any graph can be approximated by different cosine waves, and the algorithm is just solve an equation to find those cosine waves that best represent the data. In frequency domain, you will not be able to tell time, but only see the different frequencies that exist in the audio and their respective loudness. However, if you combine both frequency and time domain, you will get something cooler, the spectrogram. This purplish placent looking graph encapsulates both time, frequency, and amplitude in one graph. So it's really a three-dimensional graph, just that the third dimension, the amplitude, is represented by different shades of color, orange brighter colors being louder and purple darker colors being quieter. Something cool that I can do with this is that I can erase part of the sound just like I am drawing. So maybe you've noticed this fan noise that's been in my recording and find it a little annoying. If I want to remove that from my otherwise perfect recording, I can listen to it and looking at the spectrogram to figure out what was the frequency of that noise so that I can erase that with this eraser tool. So if I'm not careful about it, I would also clear away frequencies in my voice and make it sound funny. Now that you're familiar with sound waves and how microphone works, let's go to the light. Remember these? The Maxwell equations. Well, the only thing we need to know to understand why electromagnetic fields can travel like waves are these two equations. This one states that a change in electric field creates a magnetic field, and the other states that the change in magnetic field creates an electric field. If you want to dig deeper into them, I would recommend this video from Super One Brown and Minute Physics. Another important property of light is the so-called wave-particle duality, and it indicates that light can also be understood as photons, a particle. Let's first understand the most basic model for a camera, the pinhole camera, which just requires a small hole be poked onto a sheet of paper and for light to go through the small hole and project it onto the screen behind it. But what is it about a small hole that makes a difference? That is because when the hole is small enough, in our scale, the light at one point of the screen will all be coming from roughly the same direction in the real world. If the hole were to be a little bit larger, the light from different sources would all be able to go to the same point and make the image blurry. In the real camera though, the directing of light is done through the camera lens, which are arrangements of glass lenses. The glass in the lens uses reflection principles to achieve the same effects of the pinhole, while zoom lens gets the added feature of being able to adjust the field of view of the camera. The field of view is determined by the focal length, which is the distance between the sensor and the lens. The camera system can be mathematically represented by the camera matrix, where you put the x directional focal length here and the y directional focal length here in the matrix, and have these be the x and y location of the center point on the screen. This matrix will transform a point in the 3D world onto the 2D plane of the image, with a special coordinate system called the homogeneous coordinates. The origin of the 3D coordinate system is at the center of the camera sensor, and the origin of the image coordinate system be at the top left of the image, with the y direction pointing downwards. An interesting phenomenon around lenses is lens flare, where light coming in at tight angles will reflect on the lens instead of refracting. This creates a special looking shape in the image that's related to the shape of the lens of the camera. An interesting fact around this is that in Interstellar the movie, the VFX team was required to calculate what the lens flare would look like if an IMAX camera was filming the black hole. If you like to reduce light from the unwanted angles and reduce lens flare, a lens hood is made for just this purpose. Just like the microphone, the camera sensor also has its dynamic range and frequency range. However, the frequency range is often referred to as the color space. The dynamic range of a camera sensor is a range between the brightest and dimmest lights it can capture at the same time. The range can be shifted and adjusted by adjusting the ISO, or sensitivity of the sensor. The camera sensor perceives the count of photons that struck a pixel as the brightness of the pixel. A higher sensitivity makes the pixel brighter when only a few photons landed on it, while a lower sensitivity will make that pixel dimmer and require more photons to struck it to brighten it up. For example, we can choose to have the camera make out the difference between 10 photons and 100 photons, or we can let it make out the difference between 100 photons or 1000 photons. We want neither too high or too low an ISO, since we want to maximize the utilization of dynamic range by matching it with the range of light that we're actually getting. The color space of the camera basically determines how many different colors it can capture. A wider color space means that it will be better at capturing more vibrant colors. The last part of cameras one might not understand is the filters that the cameraman likes to put in front of the lens. These filters could be either ND filters, polarizing filters, or UV filters. ND filters stand for neutral density filters, which means that the amount of light is cut down overall without a special exception. UV filters might be the most intuitive of the three because it just cuts off the UV light that the camera sensor can receive and the human eyes cannot. Polarizing filters are the more interesting among the three. There are two kinds of polarizing filters, linear and circular. A linear polarizer filters out polarized light and helps reduce the glare in the images. A circular polarizer is a linear polarizer composed with a quarter filter at 45 degrees, which is another kind of filter that shifts the axis of the light by a quarter of the wavelength in phase, thus making the wave circularly polarized. The final bit of interesting fact about videos is the moire effect, like this, or here in my shirt. When high-frequency patterns overlap, our eyes and brains like to make out the strips of positively and negatively interfering locations, similar to beats in audio, and think that they're themselves the pattern that they're moving. And that was a lot about cameras in a single video. Hopefully you learned something about physics, waves, and cameras. I will see you next time.
This is the sound of waves.